In these next discussions, we're going to tie everything together to form Maxwell's equations, but before that, we want to go over quickly one missing term needed, or one missing piece of the puzzle needed for Maxwell's equations. So we'll call this a prequel, and that is the introduction of the displacement current. So the invention, the discovery of the displacement current is one of the key contributions that Maxwell made to tie everything together into Maxwell's equations. So it wasn't that he just tied a bunch of equations together and made it make sense, but he also filled out a missing piece that allowed the full interrelationship of electric fields, magnetic fields, and ultimately optics. So the main contribution that James Clerk Maxwell made was that he found this missing piece, which enabled us to tie these separate theories of our description of electric fields, magnetic fields, and at the time also ultimately optics, to tie these three together. So let's start by looking at what this missing piece is. So in particular, let's do a comparison of Faraday's law and Ampere's law, or Ampere Circuit Law specifically. So for Faraday's law, we have the closed loop integral, line integral of E dot dl is going to be equal to negative the change in magnetic flux going through, that should not be a closed surface integral, but the magnetic flux that's going through that surface. Separately, for Ampere's circuit law, we have the closed loop line integral of the magnetic field, H dot dl, is going to be equal to the total amount of current going through it, which would be J dot ds. So if you look at this and you're hoping to see some kind of symmetry in nature, you might see that, well, there's something missing over here, right? We'll call this question mark 1. And also, you might wish for something analogous over here. Right? We'll call this question mark 2. When you take a closer look at this, you look at question mark 1, and what would you expect question mark 1 to be? If you do this comparison, you might say, okay, this is the total amount of, if you do a closed loop of the magnetic field, you might expect current going through this. If you do the same thing through an electric field, you would expect it to be the total amount of magnetic current going through it, right? And in this case, since we do know that there's no such thing as a magnetic monopole, we're okay with any kind of, with this quantity being 0, right? Because under the assumption that there's no magnetic monopole. But what about this? And the other troubling thing here is you can see that a time-varying magnetic field can create an electric field. So if I was a magnetic field and I see this perfectly good electric field here, I can mess with it, right? If I change relative to time, I can mess with electric fields. But that's not really fair for the electric field in that, well, if I'm an electric field and there's a magnetic field over here, I'm in a bad mood, I want to mess with it, there's nothing I can do based on the equations that are here, right? And separately, there's another situation where this particular law doesn't quite work out. So let's look at a charging capacitor. So if you have a charging capacitor, you have a wire coming in, and then you have a plate, and then another plate, and then you have the other wire coming out. In between is what's in between here? This is a dielectric, right? And so there's no actual physical current going through the dielectric. However, when you're charging the capacitor acts like a short. So you actually have a current I going through. And also, not only do you have the current I going through, but you also, while this is running, you do have a magnetic field going through this. So when you're running and charging this capacitor, you have a current I going through because this capacitor acts like a short. And in the meanwhile, if you were to measure magnetic fields, you would actually have a magnetic field going around it. Yet, if you were to take some line integral that goes through this, there isn't any current that's actually going through this interface here. And so how do you reconcile that? And so this is Maxwell's primary contribution, is the conjecture that you would actually have, if you have a change in the electric flux density across a surface, across an area, that would actually create a magnetic field. So this is what he calls the displacement current. Now the displacement current has a unit of amperes. So it's just like a real current, but it is not actually, the one thing to keep in mind is that this is not actually a series of moving charges. So this is actually kind of a virtual current that has the same ability to create a magnetic field. So if you have a changing electric flux density, it has the effect of being a current in this and create a magnetic field in the same way that a real current will. And this is something that you can measure in the sense that, like I said, in say a capacitor here where you don't have actual current flow, you still have a magnetic field going around it while the capacitor is charging. Because while the capacitor is charging, the electric flux density is increasing. This is a little bit of hard to wrap your head around. Another analogy that I've heard is it's kind of like if somebody, it's the change in the electron cloud in an atom. So if these were all individual atoms and they were waving a flag, right? Or if you were just waving your hands like a soccer game, and everybody, did this motion where if this particular person waved the flag right here from left to right, and then right when this flag gets here, this other person waves the flag from left to right, and then this other person starts to wave their flag from left to right, and so on and so forth. There is actually no motion of the flag going from left to right. Like everybody's still holding on to their flag and not passing it on. They're just waving it in a particular kind of synchronous manner. And in this way, even though there's no physical movement of the flag, from the appearance of the way that the charges are moving in space, it has the effect of something like a current, which is all you need to create a magnetic field. So with this, this completes the Ampere Circuit Law into a more complete form, and that allows us to combine everything together into Maxwell's equations, where the electric field and magnetic fields can relate to each other. They can mess with each other. So like I said, changing magnetic field creates an electric field, and a changing electric field also creates a magnetic field. So that gives us two things. One is it fully ties together the electric field and magnetic field theory, but second of all is it gives a solution. It gives rise to the possibility of propagating waves. Because you can now see this situation where if I had a changing magnetic field, it will create an electric field. And if the electric field is changing over time, it will create a magnetic field, which can then create an electric field. So you can picture this opens up the possibility of magnetic fields and electric fields self-building on each other to create a propagating wave, which is what our electromagnetic communication is based off of.